So welcome to lesson 6 for exponential functions. Today we're going to learn how to graph exponential functions. So an exponential function has the form f of x is equal to b to the power of x. Again, I want to emphasize that this is the parent function. So we've seen the word parent function before. We saw that f of x is equal to x squared is the parent quadratic function. So remember, the parent quadratic function was the simplest quadratic function, and then we can apply transformations to it. Similarly, fx is equal to b, where b is greater than 0, so it's a positive number, and b cannot equal 1. So those are the constraints. So whenever you put any number here that's positive but not equal to 1, and so it's greater than 0, we see that we have an exponential function. This is the parent function. It's the simplest form. Just like with quadratic functions, we can apply transformations to the parent function. So what are some examples of exponential functions? Well, something like f of x is equal to 2 to the power of x, where again, the b value is 2. It's greater than 0, it's positive, but also not equal to 1. Another example would be f of x, which is equal to 7 to the power of x. Again, the b value is positive, not equal to 1. We can also have something that looks like this. So negative 5x to the power of x. So here you might be thinking, well, the b value is not, it looks like it's negative, but you need to keep in mind that, remember, when you have a negative and a 5 and they're not in brackets, this is actually the base. So the b value here, the 5 is still positive. The negative up front indicates a transformation. So in quadratic functions, when we had a negative up front, it changed the direction of the parabola. So if it had a positive a value, it pointed upwards. If it had a negative value, it pointed downwards. Similarly, the negative is simply here to transform the parent function of 5 to the power of x. What are some non-examples of exponential functions? Well, something like f of x is equal to x plus 3. We've seen this before earlier in the course. This is simply a line. We know that because here we have x to the power of 1. Similarly, we've seen functions that look like this. Again, because x is to the power of 2, we see that it's a quadratic function. The difference here is that the exponent itself is x. So when the exponent is x and you have a positive base that's not 1, you have an exponential function. So graphs of parent exponential functions, the b value in the exponential function, so this value here, the base, that's what the b stands for, can vary. It can either be a whole number, or it can be a fraction. So the b value, the base varies. It could be a whole number or a fraction. As long as it's greater than 0, not equal to 1, it works. This will determine the shape of the exponential curve, so what type of base it has. So we're going to look at two scenarios here. One scenario where b is a whole number, and a second one where b is a fraction. So we're going to try to graph the exponential function. For our first few graphs, we're going to use a table of values so that we know the general shape, and then we'll learn tricks and tools we can use to estimate these graphs better. So we're going to start with this first function, f of x is equal to 2 to the power of x. Again, this is a scenario where b, the base, is a whole number. So let's go to our table of values. We have x here and y. We know y is just equal to 2 to the power of x. So using the x values, we're going to plug in our x values and find our y values. So 2 to the power of negative 3, that's just 1 over 8. Again, I expect you to become more fluent with these because you've been practicing them. 2 to the power of negative 2, 1 over 4. 2 to the power of negative 1, 1 over 2, 2 to the power of 0, 1, 2 to the power of 1, 2, 2 to the power of 2, 4, and 2 to the power of 3, 8. So what you should notice is if you're more comfortable with the positive x values, you can write those in, and you'll see that the difference between the positive and the negative values is pretty much you created a fraction with whatever this value is on the denominator. So to repeat that, here, when x is 1, y is 2 because of 2 to the power of 1. When x is negative 1, it's just 1 over 2, the same answer that you got here. Okay, so here is our table of values. So based on these table of values, let's plug them in. Okay, so we have -3 1/8. Okay, that's kind of hard. Let's start with 0. These whole numbers are easier to see, and then let's deal with the fraction. So it's x is 0, y is 1. So when x is 0, y is 1 here. When x is 1, y is 2. When x is 2, y is 4. And here, when x is 3, y is 8. So we have 3 here. Let's go to 8. So again, I skipped the first 3 for now because these were whole numbers. They were easier to deal with. Now let's get back to these. When x is -1, y is half. So here's -1, half is somewhere around there. When x is -2, y is 1/4. Okay, so that's about half the distance between 0 and half, so somewhere over here. And when x is -3, y is 1/8, which is again half the distance between 0 and 1/4, which is somewhere over here. Okay, so this is the general shape of the curve. So let's connect it. When you connect it, before we connect it actually, you need to know about something called the horizontal asymptote. So what is the horizontal asymptote? I want you to take out your calculator, okay, and let's try 2 to the power of -4. Okay, so I'm just going to do this off to the side. So 2 to the power of -4, I know this one. This is 1/16, which is, again, halfway between the 1/8 and the 0. And then 2 to the power of -5, 1/32, which is even closer to 0, and so on and so forth. I want you to try a ridiculously high number on your calculator. So let's do 2 to the power of -16. Okay, so we have 1.525 times 10 to the power of -5. So that's 0.0000152. Let's try now 2 to the power of -30. It's 9.3 times 10 to the -10. So 0.00000000931. So what we see is no matter what number or negative number we put in to this x value, we never equal 0. We're getting closer and closer to 0 because each point over will be half the distance between this point and the 0, but we'll never actually reach 0. So to indicate that, we use something called the horizontal asymptote. So the horizontal asymptote, you can see that here, the numbers are getting closer and closer to 0. So we're going to put a horizontal line there, but the horizontal line would be dotted. So it's not a solid line. Okay, and this line just indicates that along the left side of this function, the points get closer and closer to 0, which is where this line is. Remember, this line is called y is equal to 0. So the points are getting closer and closer to 0, but never actually reach 0. So we call this the horizontal asymptote. So that just indicates the y values of f of x get closer and closer to 0, but will never actually equal 0. So again, we use a horizontal asymptote to indicate that because that asymptote essentially tells us that we're getting closer to that value, but we never actually reach that value. So we can see that on one side, of the exponential function, particularly the left side here, it's getting closer and closer to 0. So we're going to connect those dots to show that. So it looks something like that. Again, I've put an arrow because these points will continue on that side. But when we look at the left side of this exponential function, we see that it's growing very rapidly. Wow. We see that it's growing very rapidly. So we're going to connect those dots and again put an arrow to indicate that it continues to grow. So with exponential functions, on one half, we see that the function is kind of approaching a specific value, getting closer and closer to that value, in this case 0. Whereas on the other side, the exponential function is sharply shooting up in as a curve. So that's an example of when the b is a whole number, so 2 to the power of x. Let's answer some of these questions. So the domain, if we take a look here, there's no restriction as to what x value I can put here. This function continues this way, which means x can be any value this way. It also continues this way, so x can be any value this way, which means that the domain is x is equal, or x belongs to the real numbers. If we take a look at the range here, range, remember that's what y values you can have. If we take a look at the range, we can't equal 0, we know that because we're getting closer and closer to 0, but never actually equal it. But it can get very close to 0. It can be 0.00000000001 or other extreme examples like this. We also see that the exponential curve only exists above the x-axis, so all the y values are positive. So the way we write that is y belongs to the real numbers, but y is greater than 0. We don't put the equals because it can never equal 0. That's what the horizontal asymptote tells us. It says we can get close enough to 0, but never 0. But we see that all the points are above the x-axis, which is why it's greater than 0. We have this horizontal asymptote. The horizontal asymptote is a horizontal line. We know horizontal lines, their equation are written as y is equal to something. In this case, the asymptote was at y is equal to 0. And the curve is always increasing or decreasing. So when you are asked this question, you always read a function from left to right, just like how you read the words on a page. So when I go left to right, just use your fingers. I start down here and I keep going up and higher and higher and higher. We know that that function is increasing. So that's an example, again, of an exponential function where the b is a whole number. Now let's see what happens when b is a fraction. So f of x is equal to half to the power of x. So we have the table of values again. Again, take some time to do this. I'm going to go through it very quickly because, again, you've been practicing exponents. You should be familiar with this. I do just want to emphasize one shortcut here. So here we have our x values. We want to find our y, which is half to the power of x. Let's try this first one. So we want to find f of -3, which is equal to half to the power of -3. I want you to remember the shortcut here. We have a fraction being with a negative exponent, which means we can use the flip it rule. So flip the numerator and denominator. So 1/2 becomes 2/1. And this flip causes the exponent to become positive. So now it's just 2 to the power of 3 because 2/1 is just 2, which is equal to 8. So this is 8. Again, pause the video, write all of these down. I'm going to go through them very quickly. Okay, so half to the power of -2 is 4. Half to the power of -1, 1. Half to the power of 0 is 1. Sorry, this would be 2. I'm sorry. So half to the power of -1 is 2. Half to the power of 0 is 1. Half to the power of 1 is half. Half to the power of 2, 1/4. And half to the power of 3, 1/8. So just like before, we're given some of these numbers. Let's start plotting them. This time, these numbers look nicer. They're all the whole numbers. So let's start with that. At -3, when your x is -3, y is 8. So -3 here is here, and y is 8 there. X is -2, y is 4, so -2 and 4. X is -1, y is 2, so x is -1, y is 2 here. X is equal to 0, y is 1. When x is 1, y is half. When x is 2, y is a quarter. And when x is 3, y is 1/8. So it's similar to the graph that we've seen here, but it just looks like it's a mirror image. Like we have a line of symmetry here, and then we just flipped it over this way. So just like before, we see that one side seems to continue to increase. So we have this side here that looks like it's going to continue, or I shouldn't say increase. We have this side here that looks like it's continually going higher and higher in terms of these points as we go from right to left. And in terms of this side, we see that, again, the points are going closer and closer to a particular value. So we know that all exponential functions have horizontal asymptotes. Again, you can test it one more time. You could do half to the power of 6 and half to the power of 10. And what you'll notice is, again, you get closer and closer to 0, but never actually equal 0. So what we have here, again, is a horizontal asymptote. Remember, again, when you're drawing the horizontal asymptote, it should be a dotted line. And so on this side, it's getting closer and closer to 0. So we just draw the curve and draw an arrow. Okay, so just like before, on one side, we see values getting closer and closer to 0. On the other side, we see an area where the points are rapidly going up. Just like here, the points were rapidly going up. And here's an area where the points were getting closer and closer to 0. So based on this, again, what is the domain? There still is no restriction. X can be any value this way or any value that way. So X belongs to the real numbers. The range here, again, all of the points are above the x-axis, and we know that these points will get closer and closer to 0, but never actually equal 0. So we have what we call a horizontal asymptote. So the range, again, is y belongs to the real numbers, but y is greater than 0. The horizontal asymptote, in this case, it's at the same location at y is equal to 0. Now, when we look at, is the curve always increasing or decreasing, let's take a look. Again, when you're looking for increasing, decreasing questions, you always start from the left and go right. If I take my finger and move along the curve, I see that the y values keep decreasing. It started all the way up here, and it gets smaller and smaller, eventually getting as close to 0 as possible. So here, the function is decreasing. So if I compare exponential functions where b is a whole number with exponential functions where b is a fraction, we can see that their domains are the same. X is real numbers. Their ranges are the same. Y belongs to the real numbers and y is greater than 0. In this particular case, the horizontal asymptotes were the same. They can change as we do transformations. The difference really is whether the curve is increasing or decreasing. If you have a whole number as your base, the curve will be increasing, so it starts lower and then goes higher and higher. Whereas if your b value is a fraction, your graph is decreasing. So you start much higher and get smaller and smaller with respect to the y values. So the summary here then, if the b value of an exponential function is a whole number, the exponential curve is always increasing. Whereas if the b value of an exponential function is a fraction, the exponential curve is always decreasing. And that's the main takeaway message here. So we can see that exponential curves generally have this shape where one side is increasing rapidly or decreasing rapidly. The other side is getting closer to that horizontal asymptote, whether it be increasing here or decreasing there. So the shape of the curve seems generally similar, but whether it's increasing or decreasing really depends on whether the base is a whole number or a fraction. So let's start graphing some other exponential functions with actual transformations. So unlike lines or quadratic functions where we had specific points, for example, quadratic functions, we use the step pattern to find a minimum of 5 points and then we connected those points. With exponential functions, we actually make sketches as opposed to complete graphs. In other words, we're not going to sit there and plot different points because as the b value changes, so let me just go back to the previous example. Here, we chose our b value to be 2.5. But if the b value was 3 1/3, we'd have to know a whole new set of table of values to plot them. If this was 10 and that was 1/64, again, we need a whole new table of values to plot these figures, which is just not feasible because each new question would mean you need to get a table of values, plot them, so on and so forth. So instead, we learn how to sketch exponential functions. So we estimate the best graph for the exponential functions so that we have not the most accurate graph, but a pretty good representation of what the graph actually looks like. So when we graphed quadratic functions, we required 3 key pieces of information. Similarly, to sketch exponential functions, f of x is equal to a, b to the x plus c, we require 3 pieces of information as well. So you'll notice here that we said f of x is equal to b to the power of x is our parent function. Here we can see some transformations. We can have an a up front, we can have a c after, so on and so forth. But regardless, the 3 pieces of information we always need to sketch exponential functions are the y-intercept, the equation of the horizontal asymptote, and if it's increasing or decreasing. Once we get these 3 pieces of information, again, we can draw our best representation of our exponential function. So, example, find 3 key pieces of information for the following exponential functions and then graph them. So the first thing we need to find is the y-intercept. To find the y-intercept, you should all know this, we let x equal 0. So let's do that. We know our x is going to equal 0, so I replace my x with 0, which means on the other side, I also replace my x with 0 plus 2. So 7 to the power of 0 is just 1, so 2 times 1 is 2 plus 2, which is equal to 4. Remember, y-intercepts are always written as points. The x is 0, and the y is 4. The equation of the horizontal asymptote. The equation of the horizontal asymptote can be determined by the c value. So if you take a look up here, the value in front of the b to the power of x is your a. So this is our a value. And the thing over here is our c value. So the c value makes it super easy to find the horizontal asymptote. All you have to say is y is equal to the c value. So y is equal to 2 is the equation of our horizontal asymptote. Finally, this function is increasing or decreasing. To determine this, we have to look at our b value, and we have to remember the relationship we learned on the previous page. So remember, if the b value was a whole number, the graph will be increasing. If it's a fraction, it will be decreasing. Here, 7 is a whole number, so we know that our function will be increasing. These are the only 3 things you need to know how to do a good estimate for this graph: the y-intercept, the horizontal asymptote, as well as if it's increasing or decreasing. So you can put numbers here to help you, but you don't necessarily need to. We want to make estimates here. So let's start with the horizontal asymptote at y is equal to 2. So 1 would be around here, so 2 is here. Okay, so we're going to put our 2 there, and let's draw on our horizontal asymptote. Don't forget that horizontal asymptotes will have a horizontal dotted line. So we've taken care of our horizontal asymptote. Yes, I do want you to label or write the equation for the horizontal asymptote beside it. So that's the first thing. Now we go on to the y-intercept. The y-intercept is at 0, 4. So this is where 2 is. So 4 should be about double the distance away. So here's 4. And I'm going to put my y-intercept there. Again, I want you to label this y-intercept. So we have a horizontal asymptote, we have our y-intercept, and we know that it's increasing. If it's increasing, essentially, again, you go from left to right, you're going to go from small values to high values. We know on one side of the exponential function essentially hugs the asymptote and then moves up. So that's what we have on this side. And then on the other side of the exponential function, it just shoots up extremely rapidly. And that's our estimate for this exponential function. Again, we didn't have multiple points to go off of. It's not the most accurate graph, but it's a pretty good representation because we know exactly where the horizontal asymptote is, we know exactly where the y-intercept is, and we know that it's increasing. So this horizontal asymptote is different from the horizontal asymptote we've seen in the previous page. On the previous page, both of the horizontal asymptotes were y is equal to 0, which means as we start inputting the negative x values on this side, let me just show you the graph so it's easier to explain. So for example, here, when we had y is equal to 2 to the power of x, again, as I input negative x values, these y values got closer and closer to 0. Our horizontal asymptote here is 2, which means as I input negative x values, the y value gets closer and closer to 2. So the y values on one side of the exponential function will always get closer and closer to the c value, the horizontal asymptote, whereas on the other side, we'll see the exponential increase or decrease, depending on the b value. Okay, so I'm just going to quickly reiterate what we did. We need 3 pieces of information: the y-intercept, we need the horizontal asymptote, and to know if it's increasing or decreasing. We plotted the horizontal asymptote first. We then put the y-intercept. We knew it was increasing, so we drew a curve that was increasing. That means smaller at first and larger y values as you go. Let's try the next question, again following the same principles. So it says f of x is equal to 4 half to the power of x minus 3. So we need to find the y-intercept first. To find y, again, let x equal 0. So f of 0 is equal to 4 half to the power of 0 minus 3. Half to the power of 0 is just 1, so 4 times 1 is equal to 4 minus 3, which is equal to 1. Again, the y-intercept will be written as a point, 0, 1. To find the equation of the horizontal asymptote, again, read the instructions here if you've forgotten, but it's always y is equal to the c value, which is -3. And we need to determine if it's increasing or decreasing. To do that, let's take a look at our b value. With our b value, we see that it's a fraction this time. It's no longer a whole number. And I should actually specify that it is a fraction less than 1. Okay, so it is a fraction less than 1. And because of that, we know that it's decreasing. Okay, so now we have our 3 clues. Let's start plotting. We always start with our horizontal asymptote, which is y is equal to -3. So -1 would be here, -2 would be here, -3 is somewhere around here. Once you have that, again, put in the horizontal asymptote, and I want you to label the equation of the horizontal asymptote on the side. We're going to then plot the y-intercept, which is at 0, 1, so that's around here. Again, don't forget to label it. And the last thing is, because the b value is a fraction, it's decreasing, and so all we need to do is make a curve that's decreasing. So starts higher up and gets closer to the horizontal asymptote on the other side. So it's going to look something like this. Okay, so it starts higher up. The y values are larger, and they become smaller and smaller, so it's decreasing. Again, on one side, we see that the exponential function is decreasing very rapidly. On the other side, we see that the function is getting closer and closer to that horizontal asymptote. So again, what does this horizontal asymptote mean? As I put in larger and larger x values into this equation, the y values will be closer and closer to -3. We're going to try the last two. Hopefully you're starting to see the patterns here. This should be not hard, but it should be completely new material. So you might need to focus on it a bit more than the other units. So then we have our y-intercept here. Again, to find the y-intercept, let x equal 0. So f0 is equal to 5, a quarter to the power of 0 minus 5. So a quarter to the power of 0 is 1. 5 times 1 is 5. Minus 0 is 0. Okay? So in this case, the y-intercept is 0, 0. Equation of horizontal asymptote, again, y is equal to the c value, which is -5. And is the function increasing or decreasing? We look at the b value. Again, the b value tells us that it's a fraction. And because it's a fraction, we know that it's decreasing. Once you have this information, start plotting everything. So we start with the horizontal asymptote. Y is equal to -5. So that's around -1, -2, -3, -4, -5, somewhere around here. Again, put in your horizontal asymptote. And then label that as well. Just going to put the negative up front again because it's kind of lost in the horizontal asymptote lines. The y-intercept was 0, 0, so we can put that in. And again, we know it's decreasing, so all you have to do is draw a curve that's decreasing. If it's decreasing, it's going to start higher up, and then as it gets down, get closer and closer to the horizontal asymptote. So I'm just going to flip the page to quickly draw this. Again, something that looks like this, where it starts higher up and decreases over time, getting closer and closer to the horizontal asymptote. The last example we have here, again, follow the same 3 rules for the y-intercept. Let x equal 0. So f of 0 is equal to 2. 4 to the power of 0 plus 6. 4 to the power of 0 is just 1. So 2 times 1 is 2 plus 6 is equal to 8. The y-intercept is 0, 8. Equation of the horizontal asymptote, that's just y is equal to the c value. So y is equal to 6. And we look at the b value to determine if it's increasing or decreasing. It's a whole number here, so it is increasing. Okay, so based on these three pieces of information, let's again start by drawing in the horizontal asymptote. So 1, 2, 3, 4, 5, 6. 6 is, or sorry, I completely messed that up. That's -6. We want +6 this time. So I'm going to go up. So 1, 2, 3, 4, 5, 6. That's somewhere over here. Don't mess up positives and negatives, just like how I did. So here's the horizontal asymptote. Y is equal to 6. So let's draw that in. So here's our horizontal asymptote. Y is equal to 6. Again, label that. We have our y-intercept, which is 0, 8, which is slightly higher. So let's say around there is 8. So don't forget to label your y-intercept. And we know that the function is increasing, which means it's going higher up as time goes, or as the x values increase. So we're going to start off smaller and get larger. So when we start off smaller, it should be hugging the horizontal asymptote. It gets larger and larger, and eventually looks something like this. Okay, so again, just to reiterate what we did with these past 4 examples, is that we found the y-intercept horizontal asymptote and whether the function is increasing or decreasing. The y-intercept should be fairly easy. We let x equals to 0 and solve for it. The horizontal asymptote is always determined by the c value here, and whether it's increasing or decreasing depends on the b value. If it's a whole number, it's increasing. If it's a fraction, it's decreasing. Again, assuming that the only fractions I'm going to give you are less than 1 and greater than 0, obviously. Okay, and so once you have that, you always plot the horizontal asymptote first. Then you plot the y-intercept. You determine if it's increasing or decreasing and show that general pattern here. It's increasing, so we showed an increasing curve. If this was decreasing, we would show a decreasing curve. As long as one side of your exponential curves are getting closer and closer to the horizontal asymptote and the other one is kind of increasing or decreasing rapidly, you know you've done the right thing. Okay.